Alright, so this is video 2 for the universe, picking up where we left off. So in the last video we talked about ants on a ruler. Well, now let's take a look at a three-dimensional analogy. And a great example of this is raisin bread. So let's say a chef accidentally puts in too much yeast. So when she sets the bread out to rise, it doubles in size over the next hour. It causes all of the raisins to move farther apart. So I think you can see why this would be more of a three-dimensional analysis, where the ants was like a one-dimensional. But measure the increase in distance, calculate the speeds on the raisins and bread, just like we did for the ants on the ruler. You'll see that since the distance doubles during the hour, each raisin moves away from our selected raisin at a speed proportional to its distance. Everything is the same here. We can even do something with like blowing up a balloon. We'll see this. The two analogies are useful for clarifying our thinking, but you must not take them too literally. On both the ruler and the raisin bread, there are points that are at the edge or the end, and you can use this to pinpoint the middle of the ruler in the loaf. This is something a lot of students have trouble with. The universe does not have boundaries. There is no center to the universe. There's no edge to the universe. That's where it's strange. You cannot move to the middle of the universe. It doesn't have a middle. So what's useful to notice about both the ants and the raisins is that they do not cause their own motion. It was the stretching of the medium that moved them. So the expansion of the universe does not imply that the individual galaxies and clusters of galaxies themselves are expanding. Neither raisins or the ants in our analogies got any bigger. It was simply the medium that expanded. So, gravity that holds galaxies and holds clusters of galaxies together, and as they get farther away, without changing in size. So you don't have to worry about the Milky Way galaxy getting bigger and fluffier. That's not how that works. Another thing to, I guess, kind of a consequence of this, we measure galaxies so far away that they're traveling faster than the speed of light. And that seems to be a violation of physics. But if you remember that it's not the galaxies moving, but the space between them that is expanding, that space can expand at any speed it wants to. So it is not truly a violation of the laws of physics. So this is it's kind of like a cheat code, if you will, a way to get around the nothing can go faster than light thing. No object can travel faster than light, but space between galaxies, it is allowed to expand faster than the speed of light. And that's something that's really crazy to think about. So, now we can talk about the distribution of galaxies. So, in order for them to collide, galaxies must be pretty close together. So, to estimate how often collisions occur, how they affect the evolution of galaxies, astronomers need to know how these galaxies are distributed in space and over time. Are most of them isolated from one another? How are the galaxies and their groups arranged in the cosmos? Are there as many galaxies in one direction in the sky as another? How did galaxies get to be arranged the way we find them? These are all questions that we need to answer. So Edwin Hubble, our superstar here, did find some answers to some of these questions a few years after he first showed that the spiral nebulae were in fact galaxies and not part of the Milky Way. He made two discoveries that turned out that are very, very important. So we got to remember this. There are two discoveries that we're going to talk about here that are very, very important. The first one is called the Cosmological Principle. So this is the first one we need to talk about here. So when Hubble was working from the observatory in Mount Wilson using the 2.5 meter telescope, even a very large telescope like this one still has a very small field of view. You can only see a small part of the night sky. I mean, even the super large 10 meter telescopes or the 8-meter telescopes, they can only see a very small bit of the universe. So to photograph the entire sky with that 2.5-meter telescope, it would have taken longer than a human lifetime. There's just no way to do it. So Hubble sampled the sky in many different regions. And in the 1930s, he photographed 1,283 sampled areas. And on each print, he counted the number of galaxies. This is something anybody can do. You just count. So the first discovery that Hubble made from that survey was that the number of galaxies visible in each area of the sky is about the same. It didn't matter where he looked. He counted about the same number of galaxies. And he also found that the number of galaxies increased with faintness. So as we would expect, if the density of galaxies is about the same at all distances from us. So to help you get an idea for this, imagine you're taking pictures in a crowded stadium. The people closer to you would look big, and only a few would fit into the photo. If you focus on the people farther away, they will look smaller, and more of them will fit into your photo. As you look farther and farther away, you will be able to fit more and more people into your picture. So Hubble's findings, they indicate that the universe is both isotropic and homogeneous. So these are the two important factors here. So what does this mean? Well, it means that the universe looks the same in all directions, and it doesn't matter what section of the universe we observe, any section will look the same as any other. So Hubble's results, and many more that followed since then, and nearly 100 years of astronomy, imply not only that the universe is about the same everywhere, but also that aside from small-scale local differences, the part we can see around us is a representative of the whole, and that's what we call the cosmological principle. So by studying one bit of the universe, we can scale that up and say it must be true everywhere. That's what the cosmological principle does for us. By studying one part, we're really studying the whole. Without this principle, we wouldn't be able to make any progress at all in studying the universe. Suppose your own local neighborhood was unusual in some way. Well, then we could not understand what the universe is like if we were marooned on a warm southern sea island without communicating and trying to understand the geography of Earth. I mean, if you were stuck on a tropical island, you wouldn't know about continents. You wouldn't know about snow or large trees. And Hubble basically did this by merely counting the number of galaxies in different directions, without knowing how far away most of them were. So with modern instruments, astronomers have measured the velocities and distances of hundreds of thousands of galaxies and built up a meaningful picture of the large-scale structure of the universe. So with that, I think that's a good place to finish this video. So again, the cosmological principle is based off of two things here. The fact that the universe is isotropic and homogeneous. So those are very two important terms when it comes to understanding the cosmological principle. And again, by studying one part of the universe, we're in fact studying the whole universe. And that's very, very important to help us out. All right, so that's it for video 2.